Yes, Arun Prasad. Hello. Okay, so let me see how many members are there. Okay. Okay, so good noon to all of you. I think there are 10 persons in the meeting. So you all are taking the course CY05, right? Basics of Inorganic Chemistry. Am I audible?
Yes, sir.
Okay, fine. So you already had classes, a few more classes before this one for doubt clearing sessions. And so today we are starting with like my session will be started from today. So you attend. So can you introduce yourself so that it will help me to understand from where you come, your backgrounds. Arun Prasad. Hello, am I audible? Hello. Okay, then who else? Mahalakshmi. Hello. Okay, Bhuvanesh. Okay, you are BSc first year. And what about others? You can unmute yourself and talk. I can see Sagar. Okay, Arun Prasad, first year BSc. Sagar, you are okay. You can unmute yourself, not a problem. Okay, you are MSc. Okay, fine. So, okay, that's good. So, today we'll start here. So, what I will do in this class, I will try to cover uh, the gist of the topics that have been taught in first week. Okay, I presume that you all have gone through the first week videos, right? So four lectures were there. The many preliminary topics were introduced and discussed in these four lectures. So I will try to give a gist of that. And if you have any doubt regarding anything, you can ask me. So in that way, I will help you. Like as it is a read and class, as you know all, so it will help you to like get your doubts clear. Or if you have any suggestion or you need any help, that we can help you. That is the way we have assigned to help for the course, right? So anyone can see my screen. I will just share it. Can you see my screen?
Yes, sir.
Yes, yes.
Okay. So today we'll start uh, discussion of this course. Just a second. Is my cursor moving? Can you see the cursor?
Yes, sir, we can see, but it's not moving.
Not moving, right? There may be some time lag. Just wait a second. Okay, so today we'll start. I'm using a graphic pad, so my writing will be a little bit disturbed. So you have to bear with that. Discussion on. Okay. So let us discuss about the first lecture that was taught in the video. So have you gone through the first lecture? Anyone has gone through the first lecture? What was discussed there? Okay, so we covered actually two things. So one was Z effective or effective nuclear charge. So I will discuss the things such a way that whether you are a BSc student, PhD first year, or in MSc also, so both will understand. Like it will be beneficial for both. So that way I will discuss little bit preliminary. Okay. So you know about effective nuclear charge. Suppose you have a nucleus. Pardon my drawing. I have to get little bit habituated with this. So suppose this is your nucleus. Okay, inside you have protons, neutrons, and then you have different orbits. Okay, you here you have electrons like this, and then you have another subsequent orbits, and so on and so forth. So what you know here in nucleus, where what resides in nucleus? So what is present there in nucleus? You have protons and neutrons, right? So neutrons are neutral in charge. They have no charge. So charge is zero. Okay. I can say Q is zero. And what about the others? These are charged. This is a positive charge, right? You agree with me? Okay. So in the outer orbits, you have electrons, and these are all negative charge. So suppose Z. Z is what? Z is your atomic number, and this actually reflects how many protons you have inside your nucleus, right? Or nuclei. So this is the number of protons that is residing in the nuclei. So this has Z plus charge. Okay. And then you have electrons that are moving in the outside orbit. So this positive and this negative, it will has a attraction. Okay, so all these electrons, whatever is in the orbits, they will be attracted towards the core, right? Okay, you understand this very very preliminary things. Now,
Yeah.
okay, anyone has any question? Okay, I think somebody has unmuted his mic. So now say this is nucleus, these are the orbits. I think somebody has unmuted their mic. Can we check it? So, so you know how the orbits stay. So suppose this is your nucleus. First orbit will be 1s, then 2s, then 2p. Okay, this is according to the energy of that orbital, right? So you have a relation. You may have already seen in the lectures. So this is how it should be gone. Like sorry, it's for right here. So this someday later. So how electrons are formed like this. Okay, then so on and so forth. Okay, first 1s will be field, then 2s, then like this. So what does we get from here? 1s, 2s, 2p, 3s, 3p. Then after 3p what comes? 4s, then 3d. Okay, this is special relation between these two, 4s and 3d, so that 4s is less energy, and 3d is of high energy. Okay, I will discuss all these things. Why this is less energy, why that is high energy. Okay, there is a comparison between that. So before that, let me finish the first part. So you have different kind of orbitals. You know this S, P, D, or F. How they are determined that which is S, which is P, which is D, and which is F. So when you will be in MSc, you will study some courses about the function of orbitals. When you will study quantum chemistry, then from there you can calculate, okay, the function of each orbital, and then you can know what an orbital looks like, or orbital shape. Okay, so this is dependent on a particular quantum number that is called L. Okay, so you know there are four quantum numbers, right? N, L, M, and S. There are four quantum numbers. N is primary, L is secondary, then you have one that is called azimuthal or magnetic, then you have spin, right? So this value of L, this determines what is the shape of orbitals, right? Anybody following? If anybody has any questions regarding this? So generally what happens for S, L is 0. Okay. For P, L equal to 1. Similarly for D, L equal to 2. And for F, L equal to 3. Okay. And when it is like that, then you will get the shape of an orbital. So s orbital will look like a sphere. This is the orbital shape of s. This is for p. Okay, and d you have total 5 set of orbitals. So p you have 3 sets. So this is say according, sorry, uh, I can take this. Say this is y-axis. So this one is py. Sorry, it is not working properly. So you have 3 axes, right? So suppose this is y, this is x, and this is z. So you can have this axis. Okay, some problem. Just a second. If you have 3 axes like x, y, and z, so if your p-axis is lying like this, along the x-axis it is called px. If it is along y-axis, it will be called py, right? And if it is along z-axis like this, it will be called pz. You have 3 set of p orbitals. And d, similarly in d you have 5 set of orbitals. So you have dxy, dyz, dzx. Okay, these three, it forms a degenerate. So degenerate means same in energy. Degenerate set of orbitals. And there are two others. One is dx square minus y square, one is dz square. These are also degenerate. So anybody out of you have studied d orbitals, energy term of d orbitals? So you know you have 2 set in d. So coordination chemistry, have you studied? Anyone? Hello. You know of this term T2G and EG? Hello. Okay. So this 3 set, as I have already told you, this will form a degenerate, and this is actually the T2G part. Okay. So this comes in between the axis. Okay. And these other two, x square minus y square and z square, it is along the axis. So they are a little bit high in energy. There is an energy difference. It is also called some other steps like CFAC and okay, this will come in coordination chemistry, not right now. So they form a different energy sets. One is a dxy, dyz, dzx, and x square, y square, dz square. The shapes of these are like, so as you can know, xy plane, that means there is a y, this is x, it will be like this. Okay, there are total 4 lobes. If you have yz, then you will have like this. This is y, suppose this is z, and then it will come like this. Sorry, yeah. Similarly for xz also in between that plane, and for x square and y square it will come like this. Let me draw this first. So this is y, this is x. Okay, it will come along the axis. This will be x. So this will come along the axis. And for z square, if this is z, then this will be like a lobe towards z and a round ring in between. Okay, this is the shape of dz square. So you can see different orbitals have different shapes, right? So these actually, so this shape is nothing but the probability of electrons being found in the space. Okay, so if you have s orbital, then along this sphere, anywhere your electron can be found, or it will be, suppose this is the nucleus. So you put your electron any place over the sphere, you will find the same probability of finding it. And then if you have p and your nucleus is somewhere here, so you will find most of the electrons residing somewhere here. So it is not close to the nucleus, right? So this tells us one pattern of radial distribution. This is r, and this is I will say the probability. Okay, probability of finding electron. So if you have if you have s orbitals, then what will it look like? It will be very close to your nucleus. Suppose this is 0. 0 means the nucleus and you are increasing the R value, you are going to much higher orbits. So initially just close to the nucleus you will find a maximum probability of finding the electron. If you change this one to any other orbital, okay, suppose this is the probability and this is R value. So for P it will be much less diffuse. Diffuse means your maxima, this is the maxima, right? Maxima is going in higher R. Okay, that means if something was here, that means it was very close to the nucleus and it is going far from the nucleus. So gradually, if you have some attraction, okay, positive and negative, if they are going far, you know the Coulombic interaction, it is adverse or inversely proportional. Just a second. Okay. So this is inversely proportional, okay, to the difference or the distance between your positive and negative. So electron is going far from the nucleus, so their attraction is decreasing. Okay, and this actually this for from here comes the term Z effective. Z effective means effective nuclear charge. So what is actually seen, if you have different orbitals, suppose you have 1s, you have 2s, you have 2p, and then so on and so forth, huh? You have 3s, 3p. So for different orbitals, the electron residing in it face difference in the attraction. Okay, so this is actually depicted by, where is the cursor? Yes, Z effective equal to Z minus sigma or S. This is oblique. You can use any of the term. So this is the effective nuclear charge. Z is your atomic number or number of protons. And this is called the shielding term. And normally what is seen, there is one specific term that I missed. This is called the penetrability. Okay. So this actually relates with the function. For S you have sphere, for P you have like this dumbbell, and for D you have dumbbell or something like this double dumbbell, and for F it is so much diffuse. So when your electron cloud is diffused in space, so they are not compact. So not close to the nucleus. Okay, there comes another possibility that if you have some electrons, suppose you are measuring the attraction between this particular electron and your nucleus, but you have some electrons that are residing on the orbit that is bit lower or inside to your orbit of where you are probing that electron of your interest. So this electron has also some attraction, positive, negative, and these also have some repulsion also, because as in the orbit two electrons are staying, there will be always repulsion, electrostatic repulsion in between them. So there will be a combined effect of all of this. So if you have, suppose you have s electron beneath your orbit, so your orbit of interest, okay. So you have s electron one below your orbit of interest, and you have p electron one below your orbit of interest. So as s electrons are very compact, it will sit close to the nucleus and it will be guarding them. Okay, the shielding effect, this shielding effect is much more for s than p than d than f. You know, this is the reason I discussed, because s are much more compact, so it will guard the nucleus much more. Okay, p are diffused compared to s, so that it cannot guard. It will be diffused in space, so it cannot guard the way like s. D will be much more diffused than p, and f will be much more than that. So that is why if you have s electrons underneath your orbit, then your shielding will be much more, and you can abstract that electron much more easily. So this will eventually correlate with correlate with ionization energy. Okay, I will tell you. And then what else? Electron affinity. Okay, this kind of properties, it will correlate directly. And you have a rule regarding that, which is called Slater's rule, to determine the shielding of inner core electron. Yeah. So suppose you have uh, your orbit of interest is nth orbit, regardless of n equal to, okay, n equal to 2, 3, like that, 4, and so on. So if your interest is in nth orbit, so the other electrons apart from your electron is also having some repulsion. Okay, so for that there are two rules. One is for s and p orbits, s and p, and one is for t and f orbits. So for s and p orbit, I will first write and then I will discuss. So electron in same orbit will give a contribution of 0.35. Okay, electrons in n minus 1 orbit will give contribution of 0.85. Okay, and all electrons below n minus 1, it will give 1. And what is the difference for d and f? So electron in same orbit is same as s and p, 0.35, and electron in all lower orbit will be 1. So why is the difference between S, SP and D and F? because of their nature. So these orbitals T and F, these are much more diffused than S and P. So that so that the electrons that are residing in D or AF, it is very much shielded by the inner orbits. Okay, all the inner orbits that are down their orbit of interest. So that is why they shield much more. So we can consider this factor almost 1 for DNF. But for SNP, they are not that much diffuse. So we have to consider 0.85 for the uh, just subsequent next orbit n minus 1, and all below we can consider as 1. This is the maximum case. So with that, you can calculate for many of the atoms or ions. Okay, and calculate for any atoms or ions the effective nuclear charge. Okay, are you able to understand this? Hello, are you able to understand?
Yes, sir.
Yes, sir.
Okay, if you have any doubts, you can like ask me anytime. Okay, not a problem. And this will help you. So the way I am like discussing the things, so that you can easily solve the questions of the assignment, right? You all got the assignment one, right? So you have a deadline to
Yes, sir.
submit that also. So I will help you to like solve all the questions. I will discuss it in such a way. So this effective nuclear charge, Z effect, it depends on two things. One is called charge, and this is called radii or distance. More proper term will be distance. So this one will vary proportionally to charge, okay, Q or Z as you may like, or it will vary 1 by radii or distance. So this will be inversely proportional. Okay, this is R, right? So if your shape of molecule is getting bigger and bigger, so you have nucleus in the middle. So from the nucleus, the distance of the outermost electron, suppose here is your electron, here is your electron, the distance is increasing, and as it is increasing, it is 1 by uh, r. So your Z effective will decrease with increase in size. Okay. What else? Yes, the one thing I actually wanted you to tell, difference in 4S and 3D filling. So this was most interesting part, right? So it should be like 3D is a lower. So n value is 3. Principal quantum number 3. It is the third orbit, but 4S, its principal quantum value is 4. So it is a fourth orbit. So according to your preliminary principle, like when you start filling your orbitals, the less energy will fill first. So 3 should fill first, and this should fill second, right? This should follow actually, but this is not the actual case. Actual case is 4D fills first, and then comes 3D. So there is certainly some other parameters that is restricting 3D to fill first. Okay, so this is where the things come, as we discussed earlier. So this is sphere shape, and this is very much diffused phase. Okay, and I have told you that if it is sphere, it is more compact. and it is more penetrating. You have to make an habit of using this word penetration. Okay, so if you have more electron density in the space, if you have a sphere shape, so that is coming very close to the nucleus. So as this is very close to the nucleus, it will be more penetrating, and so it will shield more, and this is diffuse, less penetrating. Why? Because it will be far from the nucleus. Okay, it cannot come close to the nucleus. Okay, and then there will be one more effect, that is electron repulsion. So in compared in these two, 4s and 3d, if you put electron in 4s, okay, that comes much more close to the nucleus because of that um, compact nature of the shape, orbital shape. So this is one thing, and another thing is that if you have more penetrating nature of your orbital, you will have less repulsion. Okay, repulsion between the electrons that are staying inside the same orbit. Okay, you know that in s orbital you can maximum put 2, and d you can maximum put 10, right? So this is one thing. If you have more penetrating, you will have less repulsion, because it will sit uniformly, and if you have less penetrating nature, then it will be more repulsion. Okay, so it will have much more energy if you give the electron inside that orbital. So 4s, so altogether, combining all these effects, 4s becomes less energetic than 3d orbital, and that is why when electron is filling fast, it will come to the 4s, and then when it is filled, then it will come to 3d. Okay, so this is one part. Mm, huh. So there should be one question here, and when filling 4s comes first and then 3d. So when we are doing the back, like a reverse thing, when we are vacating, so this should be reverse, right? First it should go from 3d and then from 4s. Okay, this is what we expect. Okay, but actually this not happens. So this will be expected, but this does not happen actually, because when you start feeling 3d, then it becomes very less in energy. Not the initial part, when it is empty. Okay, both orbitals are empty, that time voltage is much lower, but when you start filling the 3d, then its energy becomes lower, and so that it will go, it is low. So from here it will vacate first. Okay, so we need to understand what is the reason. So already sir has discussed in the video as you have gone, but I will tell you one more again, like if you have any doubts. So you have two orbitals. Suppose you are vacating from in a d orbital and you are vacating from a s orbital. So when you remove the electron out of it, there will be a contraction. Okay, why contraction? Because you have a Z number of protons from nucleus that is exerting the attraction all the time on the electron. So from the nucleus always there is an attraction on the electron. Then when you are removing one electron here, you are removing one electron, then what will happen? Your overall number of electrons is getting less. Okay, so your charge, just a second. Yeah, let me see one time. Okay, so when you are releasing this electron, so your overall number of electron will be n minus 1 electron, but z will be the same. Hmm. Then what will happen? The attraction will increase. Attraction increase. Now you check that with S and D, if you compare, D is much more diffused than S. So if you increase the attraction, which one will be more affected, D or S? What do you say? It is already contracted. S is already contracted because uh, all the 3D systems like sphere, okay, then rectangle, not rectangle actually, cube, and a cone like that. So any 3D shape, if you reduce it with the same number of material, so sphere will have the lowest volume. You can check it. Okay, with similar amount of material, any 3D shape you make, sphere will be much less volume because it is most contracted. Huh. But d electron, as it is diffused in the space, it is not that much contracted. So if you increase the attraction, the much more effect will be pronounced for the d orbital as compared to the s orbital, right? So that is why if you release one electron, d will be participating first. So as I said here also, after start filling 3D, so if you remove one electron, the most contraction will be happening in the D and system will go to less energy. So always we have to keep in mind that two things. So one is your position on the system before you doing something on the system, like if you are adding one electron, you are releasing one electron. And one more thing is after you release that electron, what is the system is going to be? Okay, what is the effect on the system? So these things all you need to take care. So as this is going through more changes, if you release electron from D, and so D electron participates uh, more. Okay, and apart from that, some other things were taught. So some primary physical property, electron affinity, then ionization energy, electronegativity. Okay, these things were taught. So I'll briefly give an idea because already sir has told everything. So ionization energy is nothing but, so if you have an uh, material A that is in gas phase, so you remove one electron, it will be A plus one electron, right? And this will give you one ionization energy. So ionization energy means the energy given given to the system. Remember that given to system to remove one electron from it. So suppose you have A to A plus. So if you are removing one electron, minus one electron, then it is called first ionization energy. Okay, you are removing one more electron, minus one again, then A2 plus electron, right? This is called second ionization energy. Okay, now you need to take care that this ionization energy, what does it depends on? Okay, so ionization energy will be proportional to Z by R. This is similar to the Z effective that I told you. Z is your charge, Z is your, this will be charge, this will be radius. That is not good. I will take this. Okay. So suppose the periodic table you have two things. You can go from either left to right or you can go from up to down. Huh. Then if you are going from left to right, what will happen? Your period, say your orbit is not changing, like your orbital level, like your principal number is not changing. So if you are going here, you are putting the electron in the same orbit. So it was 1 here, so when you go to here, it will increase the number. Okay, so as you know, this is called S block. You have here D block, you have here P. Okay, then you have one inert atmosphere, noble gases, and inside somewhere you have separate block that is called A block, right? So in a same orbit, like in when it is constant and you are adding the electron, it will add to the same orbit. Okay, when electrons are adding in the same orbit, your radius is not increasing. Okay, radii is same along one orbit, but you are increasing the number of electrons. So that what will happen? Your Z will increase. Z is the attraction, the charge. Charge is increasing means your positive negative interaction will increase and attraction also will increase. So if Z will increase, then ionization energy will be increased. So this is how going from left to right, ionization energy increases. And suppose you are going down the period, then your R is changing. So you are adding additional orbit. So your n value is changing. N is getting higher. Okay. When n is getting higher, R is getting changed because when you are adding more orbits, your size is increasing. R is changing. So if R increases, see here, if R increases, then it will be reverse to that. So ionization energy will be decreased. This is very basic thing. Okay, this is the periodical nature of electronegativity. And then let us come to the other term. You all can follow, right? Can somebody respond? This is called electron affinity. Affinity means, okay, uh, like to accept. So when you have an electronegative like Ne minus, or you have A minus in the system, sorry, A minus in the system, and suppose it takes one electron, it gains one electron and it goes to the atom form. This is called electron affinity. And electron affinity, okay, is the acceptance of electron, and that energy is, sorry, energy is exhaust exhausted from the system. So there are two differences. If you are concerned with the electroionization energy, then we need to give this energy to the system. So system will take the energy, okay, and then it will give out electron. If you are concerned with the other one, what is my person here? Okay, if we are concerned with the another term, affinity, in that case, electron will go into the system, will give the electrons, and system will give out energy. Huh? Energy is exhausted from the system. So that things you have to take care. And let us talk about the periodical nature. Same, you have row and period. Okay. So suppose you are going from left to right in a row, then same thing would have happened. Electronegativity, sorry, electron affinity will increase. So electron affinity and electronegativity two are not same. Okay. Affinity means it has already accepted the electron, but negativity, it can, like, it is attracting the electron, but it has not accepted yet. Okay, these are two different terms. You need to take care. Uh, where is the cursor? Here. And can anybody can tell me why electron affinity increases along the row and decreases down the period? Anybody? Okay, let me tell you. So in this region, in this S block, you have mostly electropositive elements. You have lithium, sodium, potassium, magnesium, calcium, all these. So these are all singly positive. These are double positive. You have triple positive like aluminum, boron. Okay. So these are all electropositive because if they has your principal electron number is 2, how much it can accommodate? 2s2 and 2p6. Okay. So as they're in S block, their p is 0. No one has p. So only they are concerned with S. But if you have 2s1, okay, getting one electron plus one electron and getting to 2s2, and then 2s1 you are removing one electron and getting 2s0, and you have like earlier orbit 1s2. So this one is much more, okay, energy efficient. Okay, so it will tend to oxidize, it will tend to oxidize much more than reduction. So that is why electron affinity is very much for this case. Okay, you cannot give any electron to this kind of atoms or elements. So these are actually metallic. So you know all these are metallic cations. So this is one conclusion we can draw, that metal cations electron affinity is less. Now you go towards the row. Okay, you have this D. We will not discuss about D. D will be discussed during transition chemistry, transition elements, or your coordination chemistry. I will talk about the P. So you know P is mostly non-metals. Non-metals. They have 2s field 2s, 3s, 3p, whatever on your n value. So I am talking about n equal to 2 here. So 2s is filled, and your 2p you have vary numbers. N can be 1 to 6, right? In this 2p orbital, electron gain is much more easy than electron release. Okay, so suppose say for halogens, take another slide. Say for halogens, you have F minus, Cl minus, what else? Br minus, I minus. Okay, so if you give one electron, what will happen? It will take that electron and it will go to the elemental form. Okay, or actually what it does is actually forms the like diatoms. Okay, F2Cl2 Br2. So it is increase here too. Then I2 like this. So it is much more easier to keep one electron in the system than to take out one system, because as this is 2p5, it will not give an electron, never. Okay, but if it gets one electron, it will become 2p6. This is much more stable, right? So for these systems, electron affinity will be more. That is why it increases down the system. And if you increase the R value, or if you increase the N, then what will happen? So your size is increasing, so you can correlate by yourself only. Size is increasing, and then what is happening? Your attraction is changing. The attraction of nucleus onto the electron is being less, right? Now, if you have electron here, if you are adding electron here, and if you are adding electron here, so if you add electron in the first orbit, the attraction will be much more. Hmm. And if you are increasing the size, this R is more, and if you are adding one electron here, then that effect will be less, right? So as distance increases, your effect also getting less. So that is why it decreases upon increasing the orbit or n value. Understand? And one more term is there, that is called electronegativity. Electronegativity. As I told you, this is not electron affinity. So electronegativity is the ability to sorry ability to attract neighboring electron. All of you can follow.
Yes, sir.
Yes. Electronegativity is the ability to attract the neighboring electron. So it is not the electron affinity. Affinity, I told you. Affinity is an energy. Okay, it's an energy value. Similarly, this electronegativity is an energy. Okay, and it is a term that depicts the ability to attract. It is not an energy value, electronegativity, but it will resemble electron affinity because the atoms which have more electronegativity, I'll just replace it like this, will have more electron affinity. These two terms are related but not exactly same. Okay, and similarly, if you talk about the trend, it will be same as electron affinity. So along the row, it will increase. If you go to the smaller atoms, so it will increase, and along the period, if you go down, it will decrease. Okay, and Yes, yes, this is fine. If you have any questions, you can ask me at any point. Okay, one thing I did not discuss, I don't think it will be needed. So there was one curve, how R varies with the Z value. If you have followed this lecture, you may see this kind of curve and so on and so forth. So you'll start from lithium, sorry, then we'll go all along up to fluorine, then sodium, C, okay, okay. So if you can see that nature or differences is in R value if you increase the Z number. So if you increase Z in periodic table, where is the cursor? So first it will go along the row. Okay. So when it is going along the row, you are adding the electron in same orbit so that your effective nuclear charge is getting increased and you are decreasing your R radius. This is up to fluorine, the last of the element in first row. Okay. And then you are increasing the N value. N goes from 1 to 2. Okay. Then you introduce sodium. Okay, so as you are increasing one orbit, your radius will get higher. Then again you will go along the orbit, you will introduce electron in the same orbit, and then your effective nuclear charge will be more and your radius will get less. So this is a typical periodic pattern that is observed for radius along the periodic table, and this trend you can use to determine the trend for other properties also, like what I discussed, ionization energy, electron affinity or electronegativity. Okay, this can be useful to you. And what else? Huh. So this is one basic term. So I told you what an electron configuration will look like. So one is, then your 2s to p, then you will have 3s 3p, then comes 4d, sorry 4s, then you have 3d, then you have 4p, 5s, like that. Okay, so for d electrons, so actually this is followed for the p block and s block, s and p. So for s block you will have one electron configuration of your noble gas. Okay, so suppose you are in say n equal to 4. Okay, so up to n equal to 3, at the end you will have one noble gas, right? So that configuration you can write at the first. Okay, so that you can you can ignore the full configuration, you can write like that. So the initial or one down orbit, you can write the configuration or the name of that noble gas, and then you can start from the s orbital. So then you will have noble gas configuration, then ns2 np126, like that. Okay, this you can follow for p block. And For S block, only S will be concerned. There is no P. But interesting thing is for D block. D block electron configuration. Okay, so D block, normally it is like, so this thing is same, noble gas, Ng. We'll have NH2 and V6. This will be filled, I think. And then you have 3 or 4D or 5D also. Dn, n can be 1 to 10, and then 4 is 2. Sorry, the particular one, 4, 5. Yeah, like that. So better I will give by 3 only. It is understandable for most of you. So let's say we are considering the first row transition metals. Okay. So for first row it will be 3D, n, and 4s2. So as I told you, first 4s will be filled, then one by one electron will go to 3D. Okay. So suppose okay, just a second. So let's say we are having iron 2 plus. Iron 2 plus, the total electron number is actually 26. Okay, so here you have the pattern. So before iron you have one noble gas configuration, and then you have 4s2 and 3d 6. So there is a catch that actually I followed all the time. So for any transition metal, you can see there are two numbers, like two digits are there. These two, this first one, 2, you can consider always for 4s2. As you can see, 4s2 will be always filled. And for the other rest digit, this 6, you can consider for 3dn. So this n you can consider for this one. Okay, only for 2 plus state. You can verify for other one also, like if you start from scandium. So scandium 2 plus means 21. So that is noble gas. Then 4s2 3d1. And from starting 3d1 you can go up to like uh, say titanium, scandium, titanium, vanadium, chromium. Manganese you have iron, cobalt, nickel, copper, and zinc. So everything you can write, but there will be two exception actually. There will be two exception. This is I'll discuss these two. Why there is exception? So suppose normally what will be expected? Chromium is like noble gas. Then you have 4s2 and this is 24. Okay, it's atomic number. So 3d 4. We should expect this, but it doesn't happen. It doesn't stay here. So similarly, like this one also, it has 29 atomic number. So we should expect noble gas 4s2 3d9, right? But this doesn't happen. This actually stays as 4s1 3d5. This also 4s1 3d10. Okay, you know why? What is the reason behind that? Why they stay in this form? If you have 4s2 or both electrons in the s orbital, so you will have more penetration, like you will have more electron density close to the nucleus, but still they choose to have 1 in the s orbital and 5 or 10 in the d orbital. So can you predict any reason for that? Why it is so? Hello? Anyone can predict? Why is it so? You can tell like whatever you understand, you can tell, not a problem.
Sir, I think the electronic configuration becomes half
Because
filled
filled and
in the d
completely
orbital,
more
so it
stable.
becomes more stable.
So why this concept of half filled and full filled like make that configuration stable? So when it is half filled, why it is stable? Okay.
Sir, that reason I cannot.
Uh,
It's not coming to my mind clearly now.
okay. So it is true. You were right. So this is half filled.
Sir, maybe it is because of the net spin will be zero due to the pairing of electron.
No, if you have half filled for D5, you have this kind of splitting, right? If you have a D5, you will be like this. It will be not pairing of electrons. 3D10 I can consider. 3D10 it will be like this, right? Just a second. So 3D10 I can consider, but not for 3D5. So these actually come. So when you will study these orbital functions, then you can know from there that when your electron will be for d, if you have n equal to 5 or 10, it will be much more stable, the energy will be much more stable. Okay, so not here, you can study like this way. So you will find in advanced courses like when you study the orbital functions. Okay, as I told you that you have different functions for each orbital, so d will have different. Okay, from there you can get, but for time being for this course, knowing this much is enough, but later you can study. So this is one part. What else? Okay, one class was there. It's pretty basic course, but still it was being taught. So have you gone through this lecture, last lecture? Hello, have you gone through this lecture? Just a second. Yes, I think already here. So it is not that much required, but still it has been part of the course, so I will discuss some of it. So you have abundant elements on Earth. So mostly you have this oxygen, then you have silicon. Can you tell me why these two are much like maximum compared to the other? Yeah, why don't? So these are all percentage values. Okay. So can you tell me what is the reason behind this two getting the maximum abundance in Earth? Any idea? Because it is the main ingredient of our crust, right? Right? Without silica, there is nothing. Okay, anything you will find everywhere is silica. So there are different compositions, aluminum also sometimes, and then you have full of iron cores. Okay, so you can find many iron ores that you can refine or you can purify it to get your metal. You have calcium, sodium, potassium, and magnesium also. These are all present in minerals and biological systems also. Right. So you have so actually the way you get all these things in nature, you cannot use it for your any purpose. So you need to extract them, and to extract them, you need to follow some specific methods.
Can you tell one more time?
Sorry.
The last slide.
Yes, yes.
Can you
Tell me.
one more?
Yeah, you have any doubt?
Yeah, yeah. Please explain once again.
I cannot understand. The voice is breaking. Can you tell once again?
Sir, please explain one more time, sir.
Okay, okay. So why you find this silicon and oxygen maximum in your earth? Because it forms silica, right? You have heard of silica, SiOX. Okay, silica can be of many forms. So silica actually forms our earth crust. Okay, then all the rock, and inside you have this volcano and other things. Okay, all the things are formed by silica. You will find most of the silica there, and some of the times you have mixture of alumina, silica, and oxygen. So we called it aluminosilicate. Okay, so these things generally found most of the times in our crust. So that is why these are most abundant. Apart from that, you have lot of iron ores. Uh, most used metal is iron in our earth. Okay, so we have lot of iron ores considering FeO, Fe2O3, then Fe3O4. You have different names for all of this. Fe3O4 is called magnetite. This is called magnetite. Fe3O3, as far as I remember, it will be called as hematite. Okay. Some of so all these metal ions, this is important point. Thank you for remembering. So all these metal ores are actually present in oxide form. I will write in the next slide. So let me finish. Follow some specific technique. This is important point is that all the metal are present in oxidized form. Oxidized form or present as metal oxide. Yeah, that is why you can see a lot of example of this, you know, calcium oxide. Okay. Then iron I already have told. Then the other also like what else? Zinc oxide. Then not sodium, potassium, magnesium, MgO, alumina, LgO3, like that. All of the metals you will find in the nature as oxide form. So you need to somehow reduce them, reduce to metallic form. Metallic form means elemental form. Sorry, not element, atomic form. And by atomic form, I will refer to the oxidation state. Actually, it will be zero oxidation state. Okay. So here what you see for calcium, for Ca2 plus here, it will reduce. It will reduce to, it will get two electrons. And then it will join together. Okay. So someone asked, so am I able to like convince you? Is it okay for you or hello?
Yes, sir. Yes, sir.
Uh, so basically, the main thing you should remember from here is that all of the metal that are present in nature comes as oxide form, and we have to reduce them to get the atom for our use. Like any metal, you use magnesium, iron, aluminum, anything that you can use, you have to reduce them. So to basically to reduce them, we have a lot of techniques. Mostly, some of the techniques are discussed. I will just write it down here. One is the mechanical, then you will have magnetic, you will have thermal decomposition. So, in your plus two studies, do you have that chapter in your chemistry for this metal extraction? You have some basic idea about this? Let me finish this, then I will explain. Okay. Now, let me explain one by one. So, mechanical separation is nothing but what you will do, you will do some washing with any solvent. Let's say water. Okay. So, suppose you have mixture of. So, this is a physical separation. You are doing no chemical things here. You have mixtures of granules here. So, let's say you are washing them. So, what will happen? This will this will not be together. So if you wash them or dilute them, then it will be separated like this. Now you can filter it. You can filter through a member, and you can get separated these big chunks, and you will have the other one. So based on size, you can separate it. Okay, this is called mechanical thing. Then what is magnetic? So magnetic separation you can only use for the atoms or elements that will be magnetically active, right? So if you basic thing is that you have some certain number of element. So let me assume that this is active magnetically and this is non-active. Now you are applying the magnetic field. Say we generally introduce magnetic field by B. Okay. So you have a conveyor belt. Okay. Say this is one motor, this is another motor. You have a belt here that is running in between them, and somewhere here you are placing one magnet. Okay. Then when it is going, you are giving your mixture here. It will go, it will go, it will go. Then here when you are putting the magnetic field, these particles will be activated towards magnetic field. Okay. And the other one will not. So when they will be falling from here, they will not fall in the same range. So suppose one part will go here and one part will go here. So if you put something here in the gradient, so at two positions, if you put some collecting things here, so you will have, let's say, this big one here and small chunks over here. So this is based on the magnetic field. So it will react to the magnetic field. It will be attracted towards magnetic field, and so it will come at a different position, right from the non-active particles. This is how you can separate by magnetic. Thermal decomposition is what? So let me show it here. Suppose you have two things, A and B, A and B. A has high decomposition temperature, B has low decomposition temperature. So you have a mixture out of them. Take them in a container. So let's say in a box I have taken all of them. Now I am heating it. Control it. I know what is the temperature. I am slowly, gradually increase the temperature. So in the low decomposition material, it will degrade first, so it will go out of the system. It can melt, it can go to any other phase, it can go out of the system. And then at certain temperature you will have only one form of the materials. Understand? So this thing you can also refer as controlled heating. Yeah, is it clear for you? Hello, is it okay, right? So I have covered up to this. So the main thing of this is these are physical methods. Physical methods. So we are not doing any chemical things with the materials, but these three are chemical chemical methods. So I will show you in different slide. So basic thing is the same. So this is also actually reduction. Okay. So element displacement by another atom, this can be reduction. Electrolytic reduction is also part of reduction, and then high temperature chemical reduction. All these are reduction purpose. So then I will show you how to reduce it. Okay. See. Uh, have you heard about this thing that is called electrochemical series? Anyone? Anyone?
Yes, sir.
So what is this electrochemical series? Do you have an idea? Any idea about this?
So it is a series of elements which are arranged according to their reduction potential.
Hmm. Okay, good. So I will tell you. Uh, so first, let me assign these reduction methods. One will be elemental reduction, one will be electrolytic reduction, and one will be high temperature chemical reduction. So let us talk about elemental reduction. Elemental reduction is nothing but okay, it's nothing but replace one element by another according to reduction potential. You have all studied about basic electrochemistry, right? You know what is reduction potential. This standard reduction potential and reduction potential of the reaction, everything you have studied, right? Basic thing, Nernst equation. So here comes the effectiveness of this electrochemical series. Electrochemical series. So what is electrochemical series? So all of the metals, okay, are arranged in a fashion according to their reduction potential, right? So this will help us to presume that which element can replace which element. Let us write first and then I can explain. Better I will start in the next slide. I don't have, or I will start from top. So it is okay for you if I remove this too? Okay. So how does this look like? You have the elements and their reduction potential. Okay. So let me write the values also. For lithium it is minus 3.05 volt, potassium minus 2.93 volt, sodium 2.71 volt, calcium is 2.87 volt, magnesium is 1.67 volt, zinc is 0.14 volt, is 0.13, copper is 25 volt. Okay, you know what is the potential for proton, hydrogen? Hello? What is the potential for hydrogen? Standard hydrogen cell? It's zero, right? That is why it is in the middle. So we always estimate the reduction potential from this. This is the level, zero level, because the potential or the standard reduction potential of an hydrogen electron is always zero. This considered as the standard. Now, what is the applicability of this? If you have some reduction potential that is positive, that means these are very much prone to reduce. Okay, say copper. Sorry. And if you have negative, that means it will not reduce. So you have to take a couple like this. Let's say we'll take a couple. Uh, HCl plus NaNO3. Can you tell me what will form from here?
AgNO3 plus NaCl.
HCNO3 plus NaCl, but I don't think here is no oxidation state change, so we may need some other HCl plus anything. So if you react with this one, then it will form okay. It will not react. So basically the idea is that if you have two pairs, one from here, one from here, or one from here, or maybe in between anyone, just two pairs. Okay. The one which is having the higher reduction potential, higher reduction potential will replace the atom with lower potential. Okay. Basically, you can think of such a way that for which couple or for which element the value is higher, it will try to reduce first. Okay, and the other one will be oxidized. Okay, so can I give an example? So let me check. So I'll check for one. Okay, this is the main idea. You can check by yourself. So if you take two couple here, so one with the higher radiation potential will replace this one. Okay, this is the elemental one, element reduction. And if you have electrolytic reduction, in that case, so you will have electron instead of any atom. So in earlier case, what was the driving force? So suppose you have Ag in plus that is having one electron to go to Ag or AU with zero oxidation state. Okay. So this was the driving force for that reaction. Or if you have a metal, if it is releasing one electron, you can have metal plus one electron, free electron. So this electron you could have used, but here what we do actually, here we keep the electron from an electrolyte. Okay, so you have an electrochemical cell comes from an electrochemical cell. Suppose in electrochemical cell what you have, so you have two electrode. So suppose this is our system. You have some electrolyte inside. You have one anode, one cathode, okay, and you have a battery to generate the voltage. So when you put some voltage, okay, current will flow from one electrode to another, and this electrolyte here, it will uh, generate anions or cations. So it will generate ions. So that ions will help to conduct the electricity inside the solution. Okay, and this way, when this electrolyte is getting or generating ions, so that free electron that is used to reduce the oxides. Okay, and this is very much useful because you can use any metal oxide using this electrolytic reduction. Okay, so let me see if I have any example or not. Okay, so some of the systems, like when you have potassium plus, sodium plus, lithium plus, so these are very much electropositive. Electropositive means it will tend to give electrons, not to accept. So it is very difficult in natural to reduce this. Okay, but if you use these electrons, you can even reduce. You can even reduce these hardly electropositive metals. Okay, hard metals. Okay, this is the advantage of electrolytic reduction, but this is bit costly technique because as in normal reduction you can just mix some of the pairs, you can do a chemical reaction, you can replace this. But here you have to use external battery, like external voltage source, and then you have to use some costly electrodes, and you have your electrochemical setup. So this is little bit costly method, but it will give maximum output, right? So this was all from the class held in week one, and then I can discuss some of the questions. Okay, I solved the previous year questions, this year questions also, but I will not tell you all the things. I will just give you some hint. So let me discuss some of the questions. So any part you have any doubt?
No, sir.
You can reach to me. So I am PhD from IISc Bangalore. My mail ID is there. You can reach to me. Okay. If you have any doubt. Whatever time I will get, I will try to look into your query and then I can try to explain in the next class or the subsequent class I will get. So this was one question. Uh, Order of electronegativity of hybrid carbon orbitals. So we had to give the correct order. So the options were sp, sp2, then b you had sp, sorry, sp3, then c you had sp2. Okay, this was the question. So you have different hybrid orbitals of carbon, you know. sp3 is your tetrahedral, sp2 is triangular planar, and sp is linear. So what do you think? What will be the order of electronegativity as per what we have learned in this week? Okay, I may help you. So if you have any idea, you can always respond. So I will tell you sp, sp2, sp3. What we know, sp sphere is dumbbell. This is compact, this is diffused. Now, from our understanding of this first week, we know that in s orbital, electron will stay close to the nucleus, right? So it will have more attraction of the nucleus, it will be contract, right? Then p will be diffuse, so the electrons residing here, okay, will not have that much affinity towards electrons because it are not close to the nucleus. The distance is much more, right? So electronegativity means how much it can attract the neighboring electrons. If you are in S, if you give another electron, it will face much more attraction because nucleus is closer. Okay, so the more the percentage of S, more percentage of S character, more will be the attraction, right? Okay. So then it will be more electronegative. Because of the attraction, it can attract the neighboring electrons also. Then sp, how much s percentage you have? 50. sp2 how much you have? 33.3. Okay, sp3 how much? 25. Sorry, 25%, 33.3, and then you have 50. So which one according to you should be the answer? This one, right? sp will have much more electronegativity than sp2 than sp3. Okay, did you understand? Did you understand? Anyone? People are there. Okay. You can unmute yourself because from the presentation window, no, sorry, from the presentation window I cannot see it. So you can unmute and tell me. Okay. Okay. So second question was, so we had to uh, give an order, correct boiling point, uh, boiling point order of halogens. So for option ET is ET means astatine, BR Cl, astatine, iodine, BrCl, you have fluorine, iodine, Br astatine Cl, and D you have astatine, iodine, BrCl, F. So we have to give the correct boiling point order. So can you try it? I will help you also. See, these are all halogens. Halogens means 2H2 or NH2, NH2, NP5, right? It has 7 electrons in the valence shell. Now, what is changing? This part is fixed. Only this part is changing. So you are changing N from 1 to 5, right? When N is changing, you are including one more orbit. So size is increasing. Now you tell me, you are increasing the size. Or increase. Now you tell me on your understanding what can be the answer. Any idea?
Option
Option?
D.
Okay, D. And why is so? Because your R is increasing, so you are effectively increasing the size, and this size is always related to this physical properties like boiling point, melting point, decomposition, etc. Okay, so this has a clear relation with the size of the particle. So if you increase the size, automatically all these things will be increased. Okay, it's a direct relation. So that is why it will be the right answer. Thank you. This is the right answer. With increase in size, all these physical properties will increase. Let me move to another question. So these questions, okay. So this is a numerical question. Set effective for 4s if your orbital with atomic number 26 and electron configuration 1 is 2, 2 is 2, 2p6, 3 is 2, 3p6, 3d6, 4 is 2. Okay, so the options are 3.75, 6.25, and D 3.25. 325 it is. So can you try it if you have any idea? You can try it and let me know. After 2 minutes I will try. Anyone has been able to do? Can you tell me?
Option A, 3.75.
Okay, and how are you getting that?
So Z effective is equal to Z minus sigma.
Huh?
Z is 26, and
Yes.
sigma is it is a total of total number,
Yes.
uh, uh, which we can calculate from the total electron uh, for D and S, which is point three five for the electron which is present in the same
Yes.
quantum number. That means 0.35 for 4s plus uh, 14 electron in n minus 1. That means 4 minus 1 is equal to in quantum number 3, 14 electron.
Okay.
So 0.85 into 14,
Yes.
and other or other all electrons will contribute one each. That means 10 other electrons. So 0.35 plus 10 plus uh, 11.9. Though, so that total will be 22.25, which is minus from 26. Then answer is 3.75.
Okay, okay, okay. Yeah, you are okay. You are right. Okay, then I will show for the other one also. Okay, fine. But this is the exception, you know. If it was for d electrons, then just n plus one you are considered for only one. Okay, as d is very much diffused, right?
Right.
Okay, okay. Just a second. So others also got it. Okay, let me do it for others. So what I told you according to the Slater's rule. So if you have same electrons, so same orbit, each electron will contribute 0.35 per electron. You have n minus 1 orbit, you count total number of electrons and you put 0.85 per electron, and all the electrons lower than n minus 1 orbit you take 1 per electron. Okay, so this is valid for S and P. Okay, D is different. So as we have concerned only about the 4s, so suppose you are concerned with 4s, one electron. So you know in 4s there are two electrons. So one will be there. One electron will be there. So 1 into 0.35. Then you go to lower. So here you have one electron and all these three electrons you have to consider. So there are 6 plus 6, 12 plus 2, 14 into how much I told 0.85 plus this one also and this one. So as all these are below n minus 1, so you can consider all together. Okay, 10, that is my cursor, yes, 10 into 1. So this total will come as how much? 22.25. This is your sigma or s. This is the shielding. And to get the z effective, you have to subtract it from the atomic number. That is 26 minus 22.75. How much it will come? It will come 3.75. This is the right answer. Okay, everyone got it? I'll move to the second part or some other questions. Yes. This is already done. Yes. One more question on similar topic. So let you calculate this one also. Value of Z effective. It will be of very much help for you for 4s and 3D electron in vanadium atom. Okay. So these are the options: 3.75 and 4.75, 6.25, 5.35, C is 2.35, 30, and D 3.30 and 4.30. So this was the question. One thing, there is no electron configuration given. You have to write by on your own. So first, tell me what is the electron configuration of vanadium?
Argon complete 4s2 3d3.
Okay, but for this case, you need to know the electron numbers also, right? How many number of electrons? So only argon will not help in this case. So we need to write the full. So you're right. So it will be like so this is vanadium 23 is the atomic number. Then you have 4s2 3d3. But you need to write this whole configuration. So it will be like 1s2 2s2 2p6 3s2 3p6, right? And then you have 4s2 and 3d3. Okay, so for the moment I can write these like to our better understanding 3d3 and 4s2. So this is the complete electron configuration. Now you calculate and tell me what is the answer. So first you have to consider for 4s, then for 3d. So just the earlier example I have told you how to use for 4s and 3d. 3d is different, 4s is different. So after this example, we will close our class today. So just let us finish this one. So anybody has done, you please let me know. Okay.
So option
3.3
B.
for 4s.
Sorry.
Yes.
3.3 for
Hmm.
4s. That
Hmm.
means option D.
Okay. As there are no other option containing 3.3, so this will be the answer. So okay. So you can solve it by yourself, right? This is the right option. Okay, just similar way you do it like this, and I can show you for D how to calculate the D electron. So this will be the option, correct option for S, and D you have similar things. So you don't need to consider this one because it doesn't come on the n minus one range. Okay, it is n plus one. If you are concerned with the 3D, right? So there, if you consider one electron, you have two left. So 2 into 0.35, and what I told you, apart from that, so that's okay. So not 3 actually, 3, how many? 8 and 2, 10. Let us do that and then check. And here you have 10. So how much it is coming? Anyone has done this one for D? So I think anyone has completed for this one D? So let me do. So you have three electrons. If you consider one, you have left two in 3D. So 2 into 0.35 plus inside here up to here. So you have this argon configuration. Okay. From there you will get 18 into 1. Then you will get how much it is coming. 0.7 plus 18. So it will come around 15.7, and if you subtract this one from 23 minus 18.7, you will have 4.30. I think it was 0 only. Okay. So this is the right answer. So what you have to do, you take consider of this electron configuration of the earlier noble gas. Okay. So this will act as an inert core. Okay. Only you are concerned about 3dN and 4s2 for the d electrons. Sorry, considering the d electrons, not for 4s also. Okay. So take the d into account and then the inert core electron configuration, and then we will get to the answer. Okay. Understand?
Yes, sir.
Okay. So with that, let us